Let us start with a brief review of last class. Last class we looked at a p-n junction under bias. So we applied both a forward and a reverse bias and looked at the IV characteristics. We found that a p-n junction is essentially a rectifier, so that if you were to plot I versus V, this is I, this is V. The first quadrant is the forward bias, this one is the reverse. We found that in the case of the forward bias, the current goes exponentially as the voltage. Typical value of current is around milliamps. While if you have a reverse bias, we have a really small current that is of the order of nanoamps or microamps, and that is really a constant. We also wrote down the expression for the current in the case of a p-n junction. So the expression is J is equal to some constant J S naught, which is your reverse saturation current times exponential EV over KT minus 1. So this is in the case of forward bias. J S naught is the reverse saturation current, which is equal to Ni square over E E dH over LH and D, plus dE over LE and A. So dH and dE are the diffusion coefficients for the minority carriers within the P and the N region, and LH and LE are the diffusion lengths. So today we are going to start with an example in order to calculate some of these values of the current in forward bias and also the reverse saturation current. But before we do that, I want to see how this reverse saturation current will change if you change the material. So let me write this expression for Js naught one more time. Js naught is Ni square over E dH over LH and D plus dE over LE and A. Now Ni square, which is the intrinsic carrier concentration, is a material property. We know that Ni square is nothing but Nc Nv exponential minus Eg over Kt. We can substitute for Ni square in this expression, so that J, which is nothing but Js naught exponential EV over KT minus 1. So I am going to substitute the Js naught here, and instead of Ni square I am going to replace it with Nc Nv exponential minus Eg over Kt. Just for the sake of argument, and we will find out that it is true, EV over Kt is usually much greater than 1, so that I can ignore this term, the minus 1 here. I am also going to introduce another term Vg, which is nothing but the band gap divided by E. So, if you do that, J becomes equal to E dH over LH ND plus E dE over LE NA NC NV exponential E times V minus Vg over kT. So, V here is the external potential that you apply during forward bias, Vg is nothing but the band gap divided by E. So, if you were to plot the current versus voltage for different semiconductors, we find that if you want a given current, the voltage will be higher if the band gap is higher. So, let me plot I versus V for 3 materials. So, we look at germanium, silicon and gallium arsenide. So, in terms of band gap, e.g., germanium has a smaller band gap than silicon, which is smaller than gallium arsenide. Some typical values, we know germanium is around 0.7 electron volts, this is in eV, silicon is 1.1, gallium arsenide is 1.43. So, my current will be in milliamps, it is the voltage 0 So, we find that the curve for germanium comes first, then you have silicon and then finally you have gallium arsenide. So, germanium, silicon, gallium arsenide. So, that for a given value of current, so let us say I want the current to be 0.1 milliamps. The voltage is lowest for germanium, it is higher for silicon and it is even more higher for gallium arsenide, and this is because you have Vg, which is the band gap in that expression. So, let us now go ahead and look at an example of a p-n junction in silicon and calculate some values for the reverse saturation current and also the current through the p-n junction in forward bias. So, we are going to start with the p-n junction that we have looked at before. We have Na is 10 to the 17 and we have Nd is 10 to the 16th. The material is silicon, so the intrinsic carrier concentration Ni is 10 to the 10. So, we can calculate the contact potential in this p-n junction, contact potential V naught, and we did this last class. Is nothing but 0.775 volts. So, we want to know what the current is. So, we want to know the value of J when we apply a forward bias. And let me take the value of the voltage to be 0.5 volts. So, let us write down the P side and then N side. So, the first thing we want to know is how many excess carriers are injected because of the forward bias. So, from last class, if you remember, the current in the case of a p-n junction is due to the minority carriers. So, that you have electrons that are injected into the p side, you have holes that are injected into the n side, that causes the current. If you write down the values, PPO is nothing but Na is 10 to the 17th. The concentration of electrons will be just Ni square over Na, so that is 10 to the 3. Same way we can write for the n side. The formula for the excess carriers, so that Pn of 0 is nothing but PPO exponential minus E V naught minus V over kT. So, V naught here is the contact potential, V is the forward bias potential, that is 0.5. So, P and O is the excess carriers. So, if you substitute the numbers and evaluate, P and O at 0 turns out to be 2.4 times 10 to the 12 per centimeter square, per centimeter cube. So, this number is much greater than the equilibrium concentration of holes on the n side, which is here. So, this is much greater. Similarly, we can calculate the excess electrons on the p side. This is equal to 2.4 So, these are the excess electrons and the excess holes that are injected due to the forward bias. Now, these are still minority carriers. So, ultimately they will diffuse through the material, they will recombine with the majority carriers and get eliminated. So, in order to calculate the diffusion length, we need to know the diffusion coefficient. So, let me first write down the mobility. So, mu e, that is the mobility of the electron, and mu h, which is the mobility of the hole. So, mobility in the case of a semiconductor usually goes down with increasing doping concentration. So, there are standard tables from which we can get these values of mu e and mu h as a function of the doping concentration. So, once we know mu, we can calculate the diffusion coefficient, nothing but kT mu e over E. So, if I substitute all the values, this gives me the diffusion coefficient of the electrons. So, 3.1 centimeter square per second. You can also get the diffusion coefficient for the holes. This is 0.39. Now, if we want to find the diffusion length, we should also know how far or how long these minority carriers can travel before they recombine. So, we need to know the carrier lifetimes. So, let me take the values. Tau h is 417 nanoseconds, tau e to be 5 nanoseconds. So, these are again values that are known. Typically, these will also depend upon the dopant concentration. So, tau h is the lifetime of the holes that are traveling through the n side of the p-n junction. Tau e is for the electrons that are traveling through the p side. So, we can then calculate the diffusion length. So, we can substitute the values. We have dh here, we have tau h here. So, this is 21.8, 10 to the minus 3, 10 to the minus 4 centimeters, or 21.8 micrometers. Le is nothing but dE tau e, which is 1.24 times 10 to the minus 4 centimeters, or 1.24 micrometers. So, we have all the values that we need for calculating the reverse saturation current and the current during forward bias. So, Js naught we can calculate. So, you have calculated all these values, the diffusion coefficients and the diffusion length. So, we can substitute the numbers and evaluate Js naught. So, Js naught turns out is 11 ampere per centimeter square. So, this is the reverse saturation current. So, this is the current that will be flowing through if I have reverse bias the p-n junction. So, the current during forward bias is nothing but Js naught times exponential EV over kT minus 1. The voltage that we applied is 0.5 volts. So, J comes out to be 3.03 times 10 to the minus 3 amperes per centimeter square. So, this is the forward bias current. So, earlier we said that a p-n junction is a rectifier, and we can actually see that it is, because J is much greater than Js naught. In these calculations, we have assumed that the length of the device is larger than the diffusion length. So, let LH and LE be the lengths. So, this refers to the physical lengths of the p and n side. So, we have assumed that LH and LE are larger than the diffusion lengths. So, this kind of a diode is called a long diode. So that the diffusion lengths are what goes into this equation. If the physical length is actually shorter, if LH and LE are smaller than the diffusion lengths, then it is called a short diode. The only difference in the calculation is that in the equation for the reverse saturation current, instead of the diffusion lengths, in the case of a short diode, we will put the physical lengths of the P and the N side. So, let us again look at the IV characteristics, but let us look at the reverse bias side. We said that in the case of a PN junction in reverse bias, the current is a constant, does not depend upon voltage. So, we said that the current is a constant which is equal to the reverse saturation current, but it turns out at really large voltage values the diode breaks down, so that you have a large reverse current flowing through the material. So, this voltage where this happens is called your breakdown voltage. This happens in reverse bias. So, when this happens, we said that the PN junction has broken down, and there are two mechanisms for this. One is your avalanche breakdown. So, this occurs for PN junction with low doping. So, you have low doping concentrations on the P and the N side, so that you have a wide depletion region. So, if I were to draw this, P side, that is my N side, this is under reverse bias. So, in this particular case, an electron that is being accelerated by the field can essentially interact with a silicon atom, and because it has sufficient high energy because of the large external potential that is applied, that electron can ionize the silicon atom and produce more electrons. This in turn can interact with another silicon atom, so that you have an avalanche of electrons that are produced. So, this effect where the electron hits a silicon atom and ionizes it is called impact ionization. And the effect of this is that you have a large current. So, one mechanism of breakdown is called the avalanche breakdown, occurs at low doping concentrations. Another mechanism of breakdown is called the Zener breakdown. So, the Zener breakdown occurs at large doping values. In this particular case, the depletion region is thin or is narrow. So, if we were to draw the energy diagram for this, let me just draw it slightly. So, this is my P side, that is my N side. These are the Fermi levels. So, we are in reverse bias, so that there is a large barrier, but because your depletion width is small, you can have electrons tunneling from the P to the N. So, this electron tunneling is called the Zener effect. And because of that, you have a large current, so you have a breakdown of the junction. This leads to so we have looked at a p-n junction first in equilibrium and then in the case of a bias, both forward and reverse. We have also looked at the two breakdown mechanisms that are possible in reverse bias. So far in the p-n junctions we have considered the material to be the same. So, you have the P and the N type and they are both the same material. So, they could be silicon or germanium or gallium arsenide, but the material is same. The next thing we are going to look at briefly is what happens if you have two different materials, so that you have a heterostructure. So, now you have a heterojunction, so that you have a junction formed between P and N type of different materials. Once again, when we have such a heterojunction, we are going to assume that you have an ideal junction with no defects. So, this imposes a restriction on the types of materials that we can choose. In order to have an ideal junction with no defects, we must have lattice matching between the two materials, or if we want to put it in another way, the mismatch must be minimal. So, depending upon the degree of mismatch, we can control the thickness of the second layer on the first. So, if you look at epitaxial growth, the case of epitaxial growth, the layer you are trying to grow has the same lattice constant as that of the substrate, so that if there is a lattice mismatch, there is an inherent strain in the material. So, the thickness of the layer you are trying to grow is inversely proportional to the lattice mismatch. So, more the mismatch, then the thinner the layer you can grow. Ultimately, if your mismatch is large, you are just going to have a large number of defects at the interface. So, if AE is the lattice constant of the epitaxial layer, and AS is the lattice constant of the substrate, then we define mismatch delta is AE minus AS divided by AE. So, this is the mismatch. So, the thickness of the epitaxial layer that you can grow, Tc, is proportional to AE over 2 delta. So, this is an approximate expression. So, this is equal to AE square over 2 AE minus AS. So, let us take an example of silicon and germanium. So, let us say I am trying to grow a germanium layer on silicon. The lattice constant for silicon AS is 5.43 for germanium. So, that is my epitaxial layer is 5.66. In this particular case, the mismatch delta, if you try to put it in percentage, is 4%. So, it is nothing but AE minus AS divided by AE. So, the critical layer that you can grow, the thickness, if you use the formula AE square this works out to around 7 nanometers, which means you can grow a layer of germanium on silicon up to 7 nanometers. There will be some inherent strain in the germanium, but if you go beyond that, you are going to form defects in the material. In the case of germanium and silicon, you actually have island formation, and this kind of growth is called a Stransky-Krastenov growth. Instead of germanium silicon, let us say I have gallium arsenide growing on aluminum gallium arsenide or the other way round. In this particular case, the lattice constants are much closer. So, this is 5.65, this is 5.66. So, here the lattice mismatch delta is much smaller, it is typically around 0.2%. Silicon germanium, it was 4%. So, it is easier to grow epitaxial layers here. So, in the case of a hetero junction, we want to choose two materials with different band gaps. We want different band gaps because we want to exploit this difference for some interesting electronic properties, but at the same time we want a good lattice match. So, let us now look at a band diagram in the case of a p-n heterojunction. So, I am going to consider a p-n junction. So, the first, let me draw the n side, and I am going to say that the n side has a higher band gap than the p side. This is my n side. This dotted line represents vacuum. This is the conduction band, that is the valence band, and this is the Fermi level. So, I will just call this, put a subscript 1, so that this is material 1. So, we can define an electron affinity. Electron affinity is nothing but the energy from the bottom of the conduction band to the vacuum level. You can also define my work function. This is going to form a junction with a p-type material which has a smaller band gap. This is the p side. So, this is EC2, EV2, this is EF2, and once again you can write down values of chi2 and the work function. So, now I am forming a p-n junction. So, I have Eg1 greater than Eg2. I have the electron affinity going the other way and the work function also going the other way. We can also define an energy gap between the conduction bands of the two materials. So, that is delta EC. Can also define an energy gap between the valence bands delta EV. So, we want to put together this p-n junction. So, the first rule is at equilibrium the Fermi levels must line up. So, let me draw the p-n junction. So, the Fermi levels must line up. So, I have EF1 and EF2. So, I have material 1 which is my n-type semiconductor. This is the material with the wider band gap, and then I have my p-type material with the smaller band gap. So, if you look at this p-n junction, you will see that electrons go from the n to the p side. So, that there is a net positive charge on the n side, there is a net negative charge on the p side. So, the electric field goes from n to p. This is the same concept in a regular p-n junction, and we know that bands bend up in the direction of the electric field. So, the bands have to bend up on the n side and the bands have to bend down on the p side. So, we also said that there is a difference between the energies of the conduction bands, so a delta EC, and a difference in the energies of the valence band delta EV. So, when the bands bend, we must make sure that that difference is preserved, so that this gap is delta EV. Let me just extend this, and this gap is delta EC. So, now if I join these two, let me just, we can get the p-n junction under equilibrium. So, if you look at this, this is different from how a p-n junction would look if you have the same material. Specifically, if you looked at the conduction band, there is a region where there is an energy minimum, so that electrons in the p side can essentially accumulate in a region near the junction. There is a region of energy minimum, which means electrons can accumulate near that region. also the energy barriers are different for the conduction band and the valence band. So, the barriers are different for the electrons in holes. So, this can again affect the conductivity of the heterojunction. So, heterojunctions have some important properties when we look at optical properties because of the fact that you can have electron accumulation. If instead of a p-n junction where the n has a higher band gap, if you choose a p-n junction where p has the higher band gap, you will see accumulation of holes near the junction. So, with this we are done with p-n junctions. So, p-n junctions are an example where we have an interface between two semiconductors. So, they could be the p and the n of the same material, or they could be the p and the n of the different material. In next class we are going to look at devices where we have more than one junction. So, an example of such a device is a transistor. So, the next class we are going to start looking at transistors.